All right, welcome to Turning Parameter Calculation video. So in this video, we're going to figure out how to calculate the speeds and feeds and material removal time, the material removal rate, power, and we're going to learn how to draw tool paths on bar stock using carbide inserts. So step number one, let's read the question. So calculate the parameters to turn a 1.5 inch diameter mild steel bar to 1.25 inch diameter over a length of 3 inches. Use the CNMG 866-PR4315 carbide insert to carry out the calculation. So the parameters are the spindle speed, material removal time, material removal rate, and the power. Then says draw the tool paths on the bar stock. Okay, so why don't we start with B first? Because A really only makes sense if you look at what's happening, if you can visualize what's happening. So, and then we're going to write our givens. Okay, so here's our bar stock. No, I don't like that line. Let's redraw that. Okay, and it's rotating, and you want to turn it down to a smaller shape over a 3-inch diameter. So you want to end up with a shape like that. And so this diameter is 1.25, and this diameter here is 1.5. Let's say we start out with a 1.5 inch. That's what it's telling us. We were starting out with a 1.5 inch diameter. We're using mild steel. Then we're going to turn it down to a 1.25 inch mild steel and over 3 inches. Okay, so this distance here is 3 inches. Okay, so do we take one tool path? Do we take 2 tool paths? Do we take 10 tool paths? Do we take 100 tool paths? Like, do we come along here with the tool and, do we take one big cutoff? Or do we take lots of little cuts off? Like that? Well, you could do it on both ways. But there are tool recommendations that we should follow. And so it says here to use the CNMG 866-PR431 carbide. Okay, so this is where we're going to write down our givens. So this AP number here, so AP is equal to our depth of cut, and that's equal to 0.236. Now you see there's a range here. This is the smallest cut you'd want to depth you'd want to cut, and this is the largest depth that you'd want to cut with this tool. So, but this is the recommended cut that you start out with. So these in brackets are the ranges that you can go, and this is the recommended that you start off with, and then you can experiment from there. So that units are in inches. FN is our feed rate. So that's our feed. And it's 0.024 inches per revolutions. Not inches per minute, inches per revolutions. And that's because when you're programming CNC machines or CNC lathes, they're typically programmed in inches per revolution, as opposed to a mill, which would be inches per minute. So, okay, so then finally we have a surface speed for cutting steel. I've selected this carbide for steel. If I wanted to cut aluminum, I would select a different carbide. So the V surface speed for carbide, that's what the C stands for, is 1050 feet per minute. Now SFM is surface feet per minute. This is FBM, feet per minute. It's the same units, feet per minute. All right. And I've written my diameters here, 1.5, 1.25 over 3 inches. So now I think I have enough information here to start doing some calculations. So I said start with B first, because we have to figure out how many times we need to do all of these calculations. Do we need to figure out all of these parameters, differently for multiple passes? So if you take 2 paths, do we want to really calculate these if we don't have to? Let's figure out how many passes first. Okay, so really we want to know this distance here. That's the depth of the cut. So what is this distance here? That's the same distance as here, right? These are the same distance because it's all radial. And this thing's spinning. So if you cut here, you're cutting down here too. And you're cutting all the way around this whole thing. So 1.5 minus 1.25 is equal to 0.25 inches. All right. So that's the difference in diameters. But the difference in diameters is this plus this. So if these are equal, we need to divide this in 2. So 0.25 divided by 2 is equal to 0.125. Let's just make sure. 0.25 divided by 2 is equal to 0.125. Right on. So the depth of cut that I need to take to turn a 1.5 bar down to 1.25 is, or 1.25 is 0.125 inches. And this tool here says that I can go all the way to 0.236. So I'm not taking that big of a pass off, so I can go a little less. I just need to take one path. So if you were to do this question on an exam or an assignment, you would just draw a dotted line indicating your tool path there. So that's your tool path. And you could draw an arrow. So you're going to come down in front of the bar, come across, and then come up. And you'll do this whole motion in one path. So arrow for going down, arrow for going across, and then arrow for going up. And now you've completed B. Okay, so now that we know that we just have to take one pass, we just have to calculate the parameters: spindle speed, material removal time, material removal rate, and power for one pass. All right. So let's do that. So let's do spindle speed first. So spindle speed. So we know that our formula for spindle speed is N equals 12 V over pi D. I could say, well, we know this. V is equal to 1050. We know 12 and pi, we know those values. But what is D? Is it 1.5 inches or is it 1.25 inches? So I'm going to say it's 1.5 inches. And I'm not just choosing that out of nowhere. Because I want to hold this value at 1050. So if I'm cutting, so let's just draw a circle here to represent our tangential velocity, which is our surface feet per minute. I'm looking here, and this thing is rotating, and I have a point here. And it's going that fast. And I have another point here. It would be going a bit slower, and a point here would go a bit slower, and they would keep going slower and slower and slower if this thing is traveling at the same speed. So if I choose 1.25, then my speed will actually be higher than 1050 if I choose 1.25. That makes sense? So if I choose a diameter of 1.25 here, I'll draw that in green. So if I say my surface speed is 1050 at this point, then I know that my surface speed is actually higher here because the velocity is higher at the 1.5 inch diameter. So I don't want to really exceed this. So I'm just going to, and that's why I'm going to choose this to be 1.5 inches. Okay. So 12 times 1050 divided by pi times 1.5. Spindle speed is now 12 times 1050 50 divided by pi divided by 1.5. That equals 2,673. So let's call that 2,674. 2,673.8. So we're just going to round up slightly. So RPM n equal to that. Okay, so we'll put a box around that because that was the first answer. Now, let's go to MRT, material removal time. So MRT is equal to the time that it takes to cut this, to make this pass. So we're not going to actually count anything that's not cutting in this example. So just material cutting. So that is your spindle speed times your feed rate times the distance that you have to go. We'll call that L. This is going to be L. Okay, so let's just work with me here. Let's work with the units. Let's make sure that the units all work out. So MRT should be in inches per minute. Okay, so N is in revolutions per minute. FN, well, we know that it comes from the cutter information, so 0.0 inches per revolution. Inches per revolution. And L. Well, actually, we don't need L. My mistake, guys. I'm sorry. So it's just the material removal time. Need to divide by L. That's it. Okay. Divide by L. And so this is in inches. So let's cancel these out. So revolutions, cancel revolutions. This is not in inches per minute. I apologize. This is material removal time. So that's in just time. So it should just end up in minutes. And so inches deletes inches. And so we do the math here. So N, we should get 1/minute. So we'll have to divide all this by 1, and then the minutes will go up on top. So I made a mistake here, guys, again. This is not right. MRT equals length over N FN. So that's what you should be following, guys. Don't do that. I was just showing you what not to do. Sorry. Okay, so MRT is equal to 3 inches divided by 2,674 revolutions per minute. And our feet is 0.024 inches per revolution. So multiply that by 0.024 inches per revolution. Okay, so revolution cancels, and that cancels, and your inches cancel. And so you're left with minutes on the bottom. There should be a 4 there. Okay, so let's do the math here. So 3 divided by 2,674 divided by 0.024 equals 0.048 minutes. So let's just see what that is in seconds. So times that by 60 seconds per minute, and that should be about 2.8 seconds. So pretty quick cut there. That's an alarming speed. So 1 Mississippi, 2 Mississippi, 3. So that's going over 3 inches there. So it's coming pretty quick across. And so now we want to put a box around that because that's our answer. And now we need to figure out our material removal rate. So MRR. So MRR is equal to the rate at which it's cutting. So the units should be in inches cubed per minute. So our rate is our minutes and our material is in inches cubed. So this is going to be the volume of the material cut over the time that it takes, which is MRT. I'll just write that out. MRT. So that's going to be in inches cubed, and this is going to be in minutes. Okay, so how do we figure out volume? Well, we could do a bunch of calculus, so we could figure out, we could do it in disks, or we could do it in shells, whatever you want to do to figure, and you can figure out all of this material on the top and the bottom and all the way around. It's kind of like a ring, but we don't need to do that. So the volume is equal to pi d1 squared minus d2 squared over 4. So that's the difference. That will get you this area. That's just an area calculation because you're squaring your inch value. So you would get inches squared here. So that's just that area here. And then, so you want to turn that into a volume, so multiply it by L. So that's volume. So that equals. And then we have to divide the whole thing by MRT. So MRR is equal to this big monster here. Okay. Let's see if we can do this. Pi times 1.5 squared minus 1.25 squared times 3 inches. I'll divide this by 4, and we're going to divide this by 0.048. Okay, the monster, guys. So 1.5 squared minus 1.25 squared equals 0.6875. And we'll times that by pi, and we'll times that by 3, and we'll divide that by 4, and then we'll divide that by 0.048, and we get 33.7 inches cubed per minute. NRR. Okay, and we'll box that because we got the answer. So that's taken off quite a bit of material in 1 minute. Pretty good there. So the final thing to do in this question is to calculate the power. So how much power does it require to do this? Okay, so mild steel is a soft steel, so we will use, well, we have to figure out what our power calculation is, so we want to figure out power, and so power is equal to your power unit times your material removal rate. Okay, so I don't see mild steel on here, but I know that it's a soft steel, so I'm going to just make the assumption that it's got a Brinell hardness between 150 and 200, and that gives me 0.16 for PU, or unit power. So that's 0.6 times 33.7, and that equals 20.22 horsepower. So that is a lot of power. 20.22 times 7.45. That's 15 kilowatts. That how many light bulbs is that? Divide that by 60. It's 250 incandescent light bulbs. That is a lot of power. Just a lot of power. So, I hope you enjoyed doing these calculations. Yeah, so that's all required. So you'll did B, do the tool path diagram, and then you do all of the parameter calculations. So this would be quite a machine here to take this amount of material off in one go. So anyway, hope you enjoyed. Take care. Have a good night.